Hello and welcome to our CVPR 2020 oral. My name is Vít Musil and we are going to talk about optimizing rank-based metrics with Blackbox differentiation. Our aim is to directly optimize popular ranking-based metrics. Given a vector of scores, its rank is a permutation that sorts scores in descending order. Clearly, small changes in scores do not always imply the change of their ranks. Therefore, any metric that depends on ranks is, in fact, a piecewise constant function of the scores. Consequently, the gradient is zero almost everywhere, which does not allow for direct optimization. This topic has been very active lately, but proposed solutions haven't become practical. To use rank-based metric as a loss function, we have to find a meaningful gradient of piecewise constant functions. Recently, we proposed a general and mathematically sound method that enables incorporating combinatorial solvers into machine learning architectures. It turns out that ranking can be phrased as a simple combinatorial solver. We can therefore make use of the developed pipeline with very simple and efficient implementation. The Blackbox differentiation method relies on implicit replacement of the piecewise constant loss function by a piecewise affine function that respects the original one. The faithfulness of the affine interpolation to the loss is controlled by a hyperparameter. On this animation, we see a two-dimensional section of some piecewise constant loss and family of piecewise affine interpolations whose gradient is being used for optimization. The implementation is extremely simple. On the forward pass, we just compute the rank and store the data. The backward pass only needs one more rank calculation of modified input scores. So, if differentiation is resolved, can we just take a rank-based metric as a loss? Unfortunately, no. There are several other obstacles to tackle. Imagine, for instance, the point where all the scores are equal. Every possible rank can be attained in the neighborhood of such a point. This brings instability of the learning. Next, rank-based metrics are typically evaluated at this time over the whole dataset. During training, only a small mini-batch is available, which results in biased approximations. Additionally, these metrics give sparse supervision. For instance, the value of recall at k only depends on the rank of the highest ranked positive example. We propose a solution to all these issues by introducing score margin, batch memory, and designing new dense loss functions. For details, look at the paper. All this is now packed and freshly delivered to you with the name Rambo. In our experiments, we focused on two tasks: object detection and image retrieval. On detection, Rambo consistently outperformed the standard cross-entropy loss. On retrieval, we evaluated the performance of Rambo on 3 standard datasets. However, these comparisons on these benchmarks are deeply problematic, as it is nicely described in a recent paper, and so we can safely only claim that Rambo is on par with state-of-the-art with a simpler implementation. In conclusion, Rambo is the first method dealing with ranking differentiation that has all of the following. It solves the problem with solid mathematical backing, it requires minimal implementation effort, and it's blazing fast. On top of that, we identified issues independent of differentiability and we proposed solutions. Last but not least, we obtained competitive results. The success of Rambo depends on the method for Blackbox differentiation of combinatorial solvers. Ranking-based metrics can now be optimized directly. This general tool allows to use various combinatorial algorithms as neural network building blocks. For instance, according to our recent paper, it's now the state-of-the-art on deep graph matching benchmarks. Try out our code, check out our papers, and that's it. Thanks all for watching.